Hydration of cement. To master the entire concrete technology, all you just need to know is what happens when water is added to cement.
Cement powder and water react and harden through a process known as hydration. During hydration, the cement grains enter into contact with water and they begin to form a strong rods network structure, which is responsible for the final.
Before getting into details about cement chemistry, we first need to talk about cement. How is cement made? First, we need some raw materials, limestone and clays. At this stage, if you mix them with water, nothing happens. The materials don't react. What we need to get started is a little warm-up. Heat, some heat, a lot of heat. 1450 degrees Celsius to be exact. This causes the calcium from the limestone to combine with the silicon from the clays. This forms, mainly, calcium silicates.
And releases a bit of CO2.
Now that they are warmed up, if you mix them with water, they will react. Cement is a magical material. It is essentially the most practical way to make artificial rock of any shape, like homes, bridges, tunnels, and Christmas trees. It is also an excellent shield in times of war, to protect people from nuclear radiation, and against Mother Nature. It also helps us harvest energy. We've been talking about cement, but we really should have been talking about concrete.
Hydration of cement. This is one of the most important concepts of this module. Till here we have understood that how cement is produced, that how limestone or calcium oxide is undergo a wet process or dry process to form a cement, in which the major compounds are Boix compound, which is tricalcium silicate, dicalcium silicate, tricalcium aluminate and tetracalcium aluminoferrite. Now these four Boix compounds are very important for us to understand their reaction with water, to understand the hydration of cement. Now let us understand each reaction individually. The first thing is the tricalcium silicate, that is C3S, which is nearly about 45% in the cement. It reacts with the water to form the CSH gel. This CSH gel is responsible for the strength in the cement. Similarly, when H2S, that is tricalcium silicate and dicalcium silicate, react with water to form CSH gel. Along with the CSH gel, calcium hydroxide is formed, whereas the CSH gel is responsible for the strength and calcium hydroxide, which is the again another product, does not contribute anything to the strength. So till here we have clearly understood that in cement, tricalcium silicate and dicalcium silicate are responsible for the strength, because when they react with water they form the gel, which is CSH gel, which is responsible for the bonding effect. Now the two remaining Boix compounds, that is tricalcium aluminate and tetracalcium aluminoferrate, they do not add sufficient to the strength of the concrete. However, their quantities have impact on the behavior of the concrete or cement. When C3A reacts with water, it forms a compound which does not have sufficient impact on the strength. But this C3A reacts with calcium hydroxide and it is known as the sulfate attack because it deteriorates the concrete. Now here we can see that the structure of CSH gel, which form the bonding effect between the aggregates and the particles. Now tricalcium silicate and dicalcium silicate forms the CSH gel, which is nearly about to 50 to 60% of the cement volume, whereas the calcium hydroxide, which does not contribute anything to the strength, is 20 to 25%. In fact, the presence of CaOH, that is calcium hydroxide, further deteriorate the cement because it reacts with tricalcium aluminate to form a product which is not good for the strength. So these are the basic reactions that we must understand in detail to understand the hydration of the cement.
That if aluminates and sulfate react so fast, then how gypsum prevent flash setting? Or if C2S quantity is increased in cement, what will happen? Or if calcium hydroxide reduces the durability, but why? Or how can we increase the strength of the cement? And lot of other questions. This will be discovered and answered in the coming module. If you have the clarity of hydration of cement reaction, everything will be very easy.
Heat of hydration. Generally, the reaction of cement with water is exothermic, which liberates a considerable quantity of heat. This liberation of heat is called heat of hydration. Let us understand with an example. Take a small amount of cement in a flask and mix it with the required quantity of water. Now, check the temperature in the flask for a regular interval. You may notice the variation in the heat to the certain extent. The study and control of the heat of hydration are important in the construction of concrete dams and other mass concrete constructions. From the past experience, the temperature in the interior of large mass concrete is 50 degrees Celsius above the original temperature of the concrete mass at the time of placing, and this temperature is found to persist for a prolonged period. The image shown on the screen shows the pattern of the liberation of heat from the setting of cement 1:4 and during early hardening period. Once the cement is mixed with the water, a rapid heat evolves lasting for a few minutes. The initial heat evolution is generally due to the reaction of a solution of aluminates and sulfates, which is represented in the peak point A. After the while, the initial heat evolution ceases quickly when the solubility of aluminate is depressed by gypsum, which is represented by the descending peak A. The next heat evolution is due to the account of the formation of ettringite and also used due to the reaction of C3S, which is represented by the ascending peak B. Once there is less amount of unreacted cement left, the hydration of cement decreases slowly, thereby decrease in the heat liberation in the cement, which is represented by the descending curve C. At the certain point, the liberation amount reaches the lower point D in the graph. After this, the liberation of heat due to hydration is less, which process steady state condition. In general, different compounds hydrate at different rates and liberate different quantities of heat. However, if the cement product is added with retarders which alters the flash setting properties of C3A, the fineness of cement also has some influences on the rate of development of heat. However, total heat generation would be same. The total quantity of heat generated in the complete hydration will depend upon the relative quantities of the major compounds present in cement. From the analysis of heat of hydration of cement, the scientists Verbeek and Foster stated that the evolution of heat from the four major compounds of cement, which is represented in the table shown on the screen. Normally, ordinary Portland cement produces 89 to 90 calories per gram in 7 days and 90 to 100 calories per gram in 28 days. Thus, the reaction involved in the evolution of heat is faster in the early period and continues indefinitely at a decreasing rate.
Now let's conclude. The raw material used to produce cement is calcium oxide, silica oxide, we use aluminium oxide and iron oxide, also magnesium oxide, and alkalis such as potassium oxide and sodium oxide. Along with that, trisulfur oxide is also used. When it's go into the process, it forms 4 compounds known as the Bogues compound. First we have the tricalcium aluminoferrate 9%, tricalcium aluminate 11%. These two aluminate compound react immediately on addition of water. To prevent flash setting, gypsum of 3 to 4% is added. However, the byproduct of this is prone to the sulfate attack. Then tricalcium sulfate is the major compound which forms the strength by forming CSH gel. The CSH gel formed by the C3S have more quantity and less quality, whereas C2S, which is 17%, has less quantity but better quality. An undesirable COH is also formed, which does not contribute to the strength.